Well, welcome everyone to the second panel of the RCN meeting. So as Alissa mentioned, the panelists today will be looking at and discussing large-scale CO2 capture units over the world and the issues and questions that arise from that. But I will start first by giving you a brief overview within about 10 minutes regarding the various CCUS projects over the world, except for North America, since I believe John Grace will be discussing this later on. So what do we mean by large scale exactly? Well, in terms of development stage, this would be technological readiness level between 7 and 8. In terms of the amount of CO2 capture, this should be at least 0.8 megatons of CO2 per year captured if the capture unit is linked to a power generation plant, and more than 0.4 megatons of CO2 captured per year for other type of industrial activities. Also, I want to mention that I will focus mostly on integrated large-scale project, and by that I mean project that not only focus on CO2 capture, but also transportation and storage. So having set the scope, let's have a closer look at those large-scale projects. As you can see here, many of those are located in Europe and also in Asia, a few in Australia, a few in the Middle East as well, and only one in Africa and one in South America. In Europe, most of them are concentrated in the UK and in Norway. In Asia, the majority is in China, and we have 2 in South Korea. If we look at the number, these correspond to 34 large-scale projects, which has to be compared with 26 currently in the US and in Canada. In terms of trends, well, in continental Europe, we've seen a big drop in the number of those large-scale projects since 2011. This went from 14 to only 5 today. On the contrary, in China, the number has significantly risen, and now we are at 12 large-scale projects over there. Looking at project size distribution, well, as you can see on the left, the number of those projects decreases as we move to bigger size, right? And the biggest project is currently located in the UK. It's called Don Valley. It is, however, still much smaller than the largest project worldwide, which is a Century plant in the US. Many of those capture units are obviously linked to power generation, and those power plants also have a big range of sizes, and the biggest plant today is located in China. So since the beginning, you've probably noticed I've used the term project. However, some of those projects are not projects anymore and are actually being constructed, being built, or even are currently operating. In fact, the International Energy Agency has set a classification to kind of determine the stage of development of those projects. So project would be indeed project if they are at the identify, evaluate, or define stage. And once those projects are approved, then they move to the execute level, which is when they are built, and then to the operate level, which is when they're actually actively capturing CO2. So if we look at the graph here, we can see that 7 projects are actually at the execute and operate level, while the rest of the 34 are still actual projects, and most of them are in China. This is a much less mature stage than in the US and in Canada, where we count 14 projects at the execute or operate stage. It is important to note that if we want to follow the 2-degree scenario of the IEA, then we would need 30 of those projects at the execute or operate level by 2020. And right now we have 21. So this means that we need at least 9 of those projects to move to the execute or operate stage. And this is a quite big challenge given the numbers of large-scale projects that have been cancelled recently. So looking at the sectors, there are different sectors that are adopting CO2 capture at the large scale. Most of them are obviously in power generation and gas processing, and a bit less than 25 are related to other industrial activities such as iron and steel production, chemicals production, fertilizers production. In terms of the type of capture, well, the three types of capture are represented. Pre-combustion is dominant, followed by post-combustion, and then oxy-fuel combustion. In terms of the technology used, well, as we expect, solvents are dominant here with mostly amine-based solvent. It has to be noted, though, that half of the project have not yet decided on the technologies. So this is all for the brief introduction on CO2 capture at the large scale. Let's move on to the next stage, which is CO2 transportation. This is the most mature step in terms of, from a technical point of view. So as you can see here, CO2 would be transported mostly via pipelines. And this is a very important point, especially when pipelines would cross countries. Looking at the distance, well, as you can see here, most of the CO2 storage or CO2 utilization points are quite far from the CO2 capture sites. Actually, only 3 of those large-scale projects are within 25 kilometers of the capture sites. Some of those large-scale projects actually have utilization components, 32 of those projects, and all of them are referring to EOR. There are some limitations to EOR, especially considering the fact that we don't really know what's the net amount of CO2 stored, and this is because there is no systematic way of monitoring, measuring, and verifying this amount. Also, EOR tend to be a site-specific solution in the sense that you cannot have EOR sites everywhere. So that's why people, and this has been discussed a little bit yesterday, people are looking at other ways to utilize CO2 and, for instance, to make plastics, chemicals, and fuels. Nevertheless, right now, EOR can be a good economic driver to implement CO2. So the implementation of large-scale capture unit faces some challenge, which can be broadly classified as technological, environmental, and equipment-related challenges. From the technological point of view, I would like to draw your attention to the cost of the sorbent that will be used and the energy requirement when we regenerate those sorbent. The environmental challenges are related to the fact that right now there is no real legal framework to account for those emissions, and also we don't really know the environmental impact of those emissions, and we don't really know how we're going to handle the waste produced by this capture. In terms of equipment challenges, well, questions like how are we going to bring or transport all the equipment needed? How are we going to make the capture unit flexible? How can we improve heat integration? All of those questions arises. So because of those challenges, well, many projects have been cancelled. Recently, you have some examples here. And those reasons of cancellation can be broadly grouped in first funding, related to funding, so there is not enough funding or no clear financial structure. Also, the time scale is not respected. Public can be opposed to those large-scale projects. So overall, all of this is somewhat related to the fact that we may have underestimated the complexity of building those large-scale projects. So moving forward, what should we do? Well, in terms of CO2 capture, we should address the challenges I was mentioning earlier. We should also demonstrate CO2 capture at full scale for the industrial sector, because again, if we want to follow the 2-degree scenario of the IEA, then we would need 45% of the CO2 capture from this industrial sector. We also need to support more R&D in terms of new capture technology development to reduce the cost and the energy requirement. CO2 transport, well, we need to locate the future CCUS unit in order to develop the required pipeline infrastructure. We also need to provide a legal framework, especially for those pipelines that would cross countries. In terms of CO2 utilization, well, we need to identify local solution. As I mentioned earlier, EOR may not be viable everywhere, and we also need to improve the monitoring of EOR and determine the net amount of CO2 captured. So there are actually encouraging signs of people pushing for those large-scale development, and I think John Gibbons mentioned it this morning. In the UK now, if we want to build a new coal-fired power plant, this will have to come with a CCS unit. So to conclude, I would just draw your attention to the various report and database where you can find more information. So thank you all. I will invite the panelists to come to the stage, and I will introduce them. So all the panelists today will discuss various aspects of large-scale CCUS, which in the end is what we're all working for. So I believe the first speaker will be John Grace. He's a professor in clean energy at UBC and is the expert in fluid ice bed reactors.
Thank you very much. So I'm going to talk about, I was announced as talking about North American, but as I said to the organizers, I'm not an expert in what goes on in the US. I do know quite a bit about what goes on in Canada. So I'm really going to talk about what goes on in Canada, and I think that is all the time I will have. How do I advance this thing? So you should do this one here, okay. Huh? Okay, so the Canadian context I see is, according to some of these things, we as a country have huge emissions, huge energy uses. We're one of the highest in these respects, which I'm not proud of. We signed on to Kyoto in the early stages with great enthusiasm, and then proceeded to do virtually nothing. And instead of going down by 6%, which was what we were supposed to do under Kyoto, we ended up going up by more than 20% during that period. And again, I'm not proud of the performance of the country in doing that. And indeed, the Conservative government formally pulled out of Kyoto just before the end of it, having, again, done nothing to meet the terms of it. And the excuse was that they wanted to harmonize with the US, which meant, of course, doing very little. We have a particular problem in Canada, the jurisdictional problem. There's even more powers in the provincial government have been assumed by the provincial governments than in the US by the states. And in particular, there's been a long-standing battle between Alberta and the Canadian federal government over energy resources and what happens with them. And Alberta jealously guards its powers. The energy sources belong to the provincial governments. The environment is looked after within the provinces by the provincial governments, but when things cross borders, then the federal government gets involved. So it's difficult, and this causes some of our problems. At the same time, the current government has aspirations to be what they call an energy superpower, whatever that means, meaning that they want to produce enormous amounts of natural gas, and particularly bitumen coming from, depending on whether you like them or not, you call them oil sands or tar sands. Indeed, there are books out which give away very quickly their point of view from terminology that they use. But CCS formally is seen as being the crutch which is going to somehow make Alberta survive in a world where there's carbon constraints. Formally, that's what they say. Of course, as you'll see, that doesn't mean necessarily a lot gets done. So we missed our targets by wide margin, and that's despite the fact that in Canada we've really felt some of the effects of what are likely to be based on or blamed on, or can be blamed on, perhaps, climate change. Of course, can't prove any of this, but there's a strong probability that some of the things we have encountered, the melting, of course, of the polar ice in particular, we've had forest fires, we've had an enormous ice storm, we've had floods last year in 2 provinces, the pine beetle infestation in the western part of Canada, which has killed enormous tracts of trees, of pine, has led to all kinds of problems. Whoops. Let's see what we're doing here. This one, perhaps. Okay. Okay, so I'm going to come back here. So there's what we were supposed to do with our Kyoto targets and our great miss, as it was. We're supposed to, by 2020, be where we are in the red problem here, dot here. And again, with business as usual, we're not going to meet that target. There's no way we're going to meet the target. There's a slight turn down in about 2008, but that was due to the recession. And then we're supposed to, by 2050, get out to where we are with the arrows going far out to the right. And that, as you can see, is most unlikely given what's happening in the expansion of the oil sands. And here's just to give you an idea of the scale of what is happening in the oil sands. There's a truck, and you can see two people just off to the side there. So you get some idea of the scale of this. And the carbon emissions are particularly bad when it comes to the current way that they're producing the bitumen from the oil sands, which is now majority. They used to do it by mining, and those are the points in the middle. And then off to the left are the current way of doing the so-called SACD, steam-assisted gravity drainage, which uses an enormous amount of energy to produce the bitumen from it. So what you're seeing here, let's see if I can explain it to you. The gray portion is the combustion portion. When you finally end up burning the fuel that you produced from the oil sands, you produce the emissions related to the gray part. And then the red part up on top is the additional energy that goes, or the additional emissions associated with the production. And so what you see in the middle is that the arrows which are here, whoops, I'm sorry, I'm having trouble with this thing. In the middle, you see the portions related to the mining produced, thank you, mining produced bitumen. And then
I just tested it, it was working.
anyway, here it is. These two here are then what you have with the mining produced bitumen. And then way off to the left, you see the what are you doing here?
I don't mean to take up your time.
There we go. Way off to the left here, you have the production based on the SACD produced one. So enormous amounts of energy required to produce the bitumen and to upgrade it, and the carbon emissions associated with that are quite huge. Now this then shows in the blue the aquifers that underlie, in fact, all of North America, Canada, and the United States. But it happens that many of these aquifers do underlie Alberta, and so in a sense, perhaps we're a bit lucky with that, because ultimately we might be able to store a large amount of the carbon which is being associated with these. Now, pipeline proposals, of course, this is very controversial at the moment in Canada. We have such thirst to produce this oil sands in the part of the both the federal government and the Alberta government, that there are proposals for pipelines going in all directions. So we have the Keystone pipeline, which is now being debated, and which there will be a decision on by President Obama in the coming months, apparently, although they keep putting off the decision. And that will produce or ship, if it goes ahead, 830,000 barrels per day down into the US to refineries there. We have another one, which is the so-called Northern Gateway, which will go to the west coast of Canada for shipment to China, 550,000 barrels per day. We have another one going to the west coast into the Vancouver area, Burnaby refinery, which will add 590,000 barrels per day to what's already going to the west coast. And now we have proposals to go to the east coast with another pipeline, which will go to the coast of New Brunswick and for shipment to goodness knows where, probably Europe, among other places, at more than 1 million barrels per day. So if you add all that together, you have more than 3 million barrels per day being added to the more than 2 million barrels per day, which is already being produced in the oil sands of Alberta. So madness, absolute madness. And in terms of Canada meeting its commitments to various targets, it's just not going to happen. So let's look at the projects then. We've had a project at Weyburn in the southern part of Saskatchewan since the year 2000. And during its time, it was taking the emissions from a gasification plant in Beulah, North Dakota, crossing the border and being used for enhanced oil recovery. Cenovus is the company involved. It was being used for enhanced oil recovery, as I think I mentioned. And in 2000, as recently as 2008, it was the world's largest CCS project. So it generated considerable data. And there was an incident in 2011, which is rather interesting for some of the things that were talked about this morning. There was alleged to be leakage. There were a couple of farmers in the area who said that they had CO2 bubbling up in their land, and this made international headlines. So there was widespread fear being caused by this. They did a major study, but a year later they reported the result, which was that this was not anthropogenic CO2, it was biogenic. But of course this got buried in some late pages of local newspapers, and so the public perception was that there was a major problem with this. The overall capacity, 20 million tons of CO2. Put that against the 700 tons CO2 we're producing per year in Canada. It's very, very small. Nevertheless, it was a significant project and led to some findings. The Quest project, a major project which is going ahead, and this is Shell, mostly with 60% Shell with Chevron and Marathon, about 20% each. Fort Saskatchewan, just north of Edmonton. It involved oil sand bitumen. And the interesting thing about this is that this will go into a deep saline aquifer, which is a first. It won't be enhanced oil recovery. And you see the public funding involved here, considerable subsidization by Alberta and by the Canadian governments. Total cost $1.3 billion, including 10 years of operation, and it's expected to start up next year. We have another big project, the Alberta Carbon Trunk Line. The idea is you will pick up the CO2 being emitted from a number of big projects, and you will put those into a huge pipeline and you'll ship them off to a site where you can then put them underground. And so this is a 240-kilometer pipeline. It's going to compress and gather these emissions and bring them to the Lacombe area, which is further south, where it can ultimately store 14.6 million tons of carbon dioxide per year, which is being called the world's largest CCS project, but it will start out just taking a little bit of about 1.5 million tons per year, and so it'll take a long time before it gets there, if ever. Public funding, again, huge amounts of public funding required to make this work. Boundary Dam project in Saskatchewan, just to the east of Alberta. A Sask Power utility, a coal-fired power plant near Estevan. And there's your funding, again, $1.3 billion required to do this. A part of it coming from the Canadian federal government. Capacity about 1 million tons per year, and again, EOR to be used. They're also building a facility for doing some testing. Now, if I'd been talking to you in 2011, I would have been talking about 7 projects. 4 of them I've just covered. 2 of them have since been canceled, and I think it's instructive to look at why they were canceled. Despite the fact that in the Pioneer project, there was $436 million committed from Alberta, another 342 from Ottawa. It was canceled in April of 2012. They are paying a very small carbon tax that they're paying of $15 per ton, and they had these huge subsidies. Nevertheless, even with these things, it was uneconomic, and they issued a statement simply saying, we still believe there is a future for CCS, but not for us. Swan Hills, another project which was committed, was thought to be committed in 2011, it canceled in 2013, despite, again, big public subsidies. It was to have captured CO2 from a coal to syngas plant north of Edmonton, and what they blamed in their case was the low price of natural gas. So, whereas we thought we were going ahead with 7 projects, the 7th, I should mention, is still being considered, but probably not going to go ahead unless there's a major change in natural gas prices. That's in the northeast part of British Columbia, the Spectra project, so-called, but this will, again, probably not go ahead in the future. So I'm going to stop there. I have some slides I could talk about Carbon Management Canada, but I think that's a place to stop. I will mention, however, one other thing, which was that in Carbon Management Canada, we had a project which was to go ahead south of Calgary, a place called Princeton, where we were going to be putting a very small number of tons per year of CO2 down and doing monitoring and verification on this. And local farmers, even though they weren't very close, were so upset by this that ultimately it was canceled. And we've had to take that project and go way to the east of Calgary to a place called Brooks, Alberta, where there are really only people who were involved in the oil and gas business, and we have a site there where this will now go ahead. But the NIMBY syndrome is real. We're not anywhere close to the coast as you are in Britain, where you can put it under the offshore places, and this is going to be a major problem when it comes to locating CCS projects. So I'll stop there. Thank you.
So our next speaker is Roger Aines. He's a program leader at Lawrence Livermore National Lab, and his current research focus is on CO2 capture and production of clean fuels.
Thank you, Camille. I'm going to talk about a few specific examples of storage and large scale and what we've learned from those and where we might be going in the future with them. And I want to summarize those lessons here for you quickly. The first is that with the experience that we've had so far, we can say that it's safe and economical to store carbon dioxide underground. From my personal perspective, I can tell you I'm a geochemist, and I can tell you that geochemistry turns out to be not that interesting for underground storage, which is to say that we had all hoped early on that we might be able to demonstrate that mineralization underground occurred rapidly and that you were going to basically turn injected carbon dioxide into limestone. Turns out that probably does happen, but not in the lifetime of our species. So it's going to be a very long-term thing. The injected carbon dioxide goes underground and stays carbon dioxide. But on the other hand, we've learned that geomechanics is extremely important, that the mechanical behavior of the rock and the operator's behavior is very important in safe storage. So let's first look at Sleipner. We're pretty familiar with Sleipner, of course. This is the great hope of Europe, the Utsira Formation in the North Sea. It's a sandstone. It's very permeable. It's about as permeable as beach sand. You can imagine how well that will absorb things. And it's been operating for 15 years and very successfully. The people at Statoil did a good job. They started off strong and they have stayed in the game and they've done a great job. And I like to say, if you think CCS is a good idea, you should thank a Norwegian, because without them, it wouldn't be happening. The ongoing storage there, the original conception was that in this sandstone rock, we're going to inject the CO2. As you see, deep in the gas is actually produced at a very deep layer, and the CO2 is stored at a relatively shallower layer. But we thought that when we injected the CO2, it was going to rise through this formation and form something you might think of as a champagne glass shape, where the CO2 would rise in a bubble up against the cap rock. And so the first important lesson here is that it didn't really happen. The Earth is much more complicated than that. And these are seismic images of the CO2. You can think of these as images of where the CO2 is in that sandstone. And what you see are a series of layers. There we go. A series of layers that represent the CO2 being trapped in the various layers in the rock, which aren't that different from each other, but they're enough different to hold up the CO2 on its way. So instead of a champagne glass, you get this distributed set of layers in which the CO2 is being held up. It turns out that's good because that allows us to put more CO2 into the formation. It's distributed through more of the formation. But that segmentation and flow, I think, is going to be important in all these things. We think about having a big bubble of CO2 underground. It's not. It's really distributed in a whole bunch of layers and in a wide range. So it was a good start. No leakage, continuous operation. The monitoring has been very effective. This line shows you the injected amount of CO2 and then the prediction that they get from both the seismic and gravity measurements of how much CO2 is stored in the formation, and they're coincident. In other words, their monitoring is accurately telling you how much CO2 is stored down there, which is good because underneath the North Sea, it's not that easy to do much monitoring. You're not going to walk out there and make a measurement, so you better be able to do it with remote methods, but the good news is they seem to be working. Insala was the next big project that I want to talk about. Million tons a year separated from natural gas, same as at Sleipner, and being injected again into the aquifer. In this case, they're injecting it into the same aquifer that the gas is coming out, but in the gas leg, which is to say a long way away from where the gas is. And there were gas production wells in the gas part of the formation, 3 carbon dioxide injection wells, in that this is called the water leg, for those of you. And the story here is not as positive as Sleipner. As soon as we started injecting, we realized that the ground was being lifted by the injection. And when I say lifted, I mean on a range here, this is millimeters, so basically a centimeter of uplift was detectable on the desert over top of the injection wells. And you could detect this by satellite radar interferometry. Pretty easy to do in the desert, pretty accurate measurements. And that was completely unexpected and really not coincident with any of the models that were there for storage. And so BP and Statoil, to their credit, immediately formed a research consortium to figure out what was going on there. And the result is shown down below here, that basically what happened is there's a fracture above the reservoir. And the fracture does not penetrate the cap rock. The fractures, we're not exactly sure what it is. But as that fracture opens up, it forms this double lobe in the ground above that you can measure with the satellite. As soon as it was clear that, in fact, there was a fracture there, they stopped operating the site after about 3.8 million tons had been injected. And I want to emphasize that that is safely contained. The monitoring did a good job here of telling us that there was a problem. There's no leakage. The operations are now complete. I think we all know what that means. But for those of you who are not fans of underground storage, you might look at this and say, oh, this is a condemnation of underground storage. But I encourage you to recognize that this is why we do large-scale demonstrations. There are things that we don't know that you're going to find out. And fortunately, we were able to find them out here in a way that was completely safe and there wasn't any operational difficulty. And we'd rather that nothing ever failed, but every once in a while it does. And the good news is it failed safely here. Third project that I want to talk about is Snøhvit. We're now back to offshore, no longer in the North Sea, but far north of that. This is the northern end of Norway, and Snøhvit is offshore of Hammerfest, which is in northern Norway. It's another natural gas project where they're separating CO2 and re-injecting it. In this case, they bring it onshore, do the separation onshore, and then pipeline it back offshore. There are no structures out there. Everything is a sub-ocean completion. There's just completions on the seafloor, so there's no platforms or anything to be seen there. This one had an interesting history early on. These are the pressure records from the injection at Snøhvit. And it started rising, and then they stopped injecting, and it dropped. They started injecting again, it started rising. And there was a lot of discussion early on about what was going on at Snøhvit. Why is the pressure rising like that? And the answer turns out to be, again, the geology is real, and it's compartmentalization within the reservoir. This is the geophysical image of the reservoir before they started injecting CO2 into it, showing the more permeable zones. And this is just a stream channel. For those of you who are familiar with geology, this is a permeable stream channel. And they put the injection well in the middle of it. And now this image during the course of CO2 injection shows where the CO2 is going now. It's a little different use of the same color scale. But the CO2 is going into that permeable channel, which is not spreading out radially. It's not, there's less area to go into there than if the CO2 was spreading into the entire formation. This is now a map view. We're looking down on the site there, sorry. And so that's why their injection pressures were going up too high, because the CO2 simply couldn't flow away along that path as fast as they wanted it to. So Statoil solved that problem by recompleting the well in a different formation. They moved up in the formation, recompleted it. It's now flowing quite freely, and they're having no issues with that completion. So again, I would call that a great success. But we come back again to my first learning that the flow's channelized. That's going to be an important thing. But I think I can argue that with modern methods, we have a pretty good way of telling where the flow is going to go. And even to the extent that we use them, we're able to predict where the flow is going to go. And the CO2 is now being all safely stored in this higher unit, which Statoil is probably going to inject there for about another 6 or 8 years, and then recomplete in yet a third location, because they want to complete extracting the gas from the unit that they're currently injecting CO2 in the water leg. So, question you might ask is, why aren't there more large demonstrations like this? And as we just saw from Camille's presentation, there's quite a few. The number is growing. We'd all like this big ramp up to be occurring now, but it's not. This is, we're sort of hoping that that big ramp up is going to occur, but as Camille showed you, these are in the still project definition stage. But in the United States, anyway, one of the big hindrances of this is that instead of storing CO2 underground, we want to use it for oil recovery. And the reason we want to use it for oil recovery is because we can get an enormous amount of oil. If we use CO2, the current DOE extrapolation is that we could recover about as much oil from the United States as ever been recovered from the United States. So the drive to use enhanced oil recovery using CO2 is gigantic. And so there isn't a lot of pressure to just put the CO2 underground and throw it away when you could presumably use it for this distinct purpose. And there's a lot around the world, there's a lot of projects coming online that are doing the same kind of approach. Mongstad probably shouldn't be there anymore since they've now canceled it. But there's a lot of large projects coming online. I think the learnings are going to be evolving rapidly. But the $30 a ton of value means that the first thing that's going to happen is enhanced oil recovery. And I added this slide. Yesterday we were talking about what's going on in the United States. There was the implication that there weren't large projects in the United States. There's a lot of large projects either in final definition stage or in construction or even nearing operation. And the ones I've colored blue here are the ones that are all more than 1 million tons a year, and they're all putting their CO2 into enhanced oil recovery. It's a lot of work going on there. And only Future Gen, which I don't personally believe will ever be built because of problems with basically getting that project put together, only the Archer Daniels Midland project in central Illinois that's capturing carbon dioxide from fermentation of corn is actually putting CO2 into an aquifer for storage in the United States. Thank you.
So the next speaker is Pat Brady. He's a senior scientist at Sandia National Lab, and he has expertise in CO2 storage and wastewater treatment.
Thank you, Camille. Well, I want to start by thanking Alissa and Klaus for having me here. I've been fortunate to work with Alissa for the last 4 years on mineral carbonation. These results are starting to come out, and you'll see several of them out in the halls and the posters, and I would urge you to go look at them. Now, one of the other things that we work on at Sandia, in addition to carbon capture and carbon sequestration, is the DOE cleanup of hazardous waste sites and the licensing of nuclear dumps. Now, I would make the point to you all, and it's been made by my predecessors, that there are a number of parallels here. Although radionuclides are not CO2, there are a number of common themes that I want to point out to you, and I'll also suggest some solutions. First, I want to put it into context. If you go to Google and type in stupid questions in national parks, you'll come up with a list of really dopey questions that clueless tourists have asked the national park rangers. For example, there's the lady that got to the edge of the Grand Canyon and said, well, where are the president's faces? Thinking it was Mount Rushmore. Or the guy that was at the Everglades who said, is there a limit on the number of baby alligators I can bring back home to Long Island with me? Well, my two favorites came from my home state of New Mexico, where there's Carlsbad Caverns, where someone asked, well, how much of the cave is underground? And then a lady asked the park ranger who had told her all about the bats and the stalagmites and stalactites. And she said, okay, you've told me all about what's in the discovered part of the cave. Now can you tell me what's in the undiscovered part of the cave? Well, that's actually where we are with CCS right now. Let us assume that we had lowered carbon capture costs to the point where this was economically doable. How do we move forward? What happens when we move into this next realm? Some of the lessons that we've learned at DOE in the cleanup at Yucca Mountain and at the WIP site, they apply here. And I'll tell you what they are right now. Number one, we cannot ignore long-term monitoring. Number two, we cannot assume technical consensus. Three, if we are to be successful, we must expect and prepare for failure. Now let me start off with the long-term monitoring. The budget for the cleanup of the DOE hazardous waste sites is several $100 billion. Okay? This is a vast public transaction. Yet when you look at the budgets, where they look at, well, do we do air sparging, or do we dig up sites, or do we do soil incineration, God forbid, the thing that's often left out is the long-term monitoring cost. Yet when you do the full life cycle analysis, long-term monitoring is everything. This echoes a point that Klaus made this morning. This is something that people tend to ignore, is long-term monitoring. The fact that EPA has stepped forward and started to give us kind of what they're starting to expect, that's more than just of tangential interest. Those monitoring requirements are going to be absolutely critical to the economic viability of these projects. And you know, how do you solve them? Well, one way to solve them is to change the funding mechanism. The long-term monitoring at the DOE sites, well, that would come up to congressional appropriations every year. Well, if you're monitoring for radionuclides with half-lives of hundreds of years, that's probably not the best thing to do. It certainly doesn't build confidence in the folks nearby. Bonding is obviously a direction one ought to consider. Now, for Yucca Mountain was going to be this country's high-level nuclear waste repository. The license application, when we finished it in 2006 or 7, it didn't go into a FedEx package. It didn't go into a FedEx box. It went into a FedEx truck that went to the Nuclear Regulatory Commission. That wasn't the way it began. Early on, there were multiple sites, and we never expected the amount of technical effort to go into Yucca Mountain that ultimately did. There are two lessons from Yucca Mountain. One of them is to have multiple sites. I take it back, there's three lessons. One, have multiple sites. Two, do not get caught in the trap of looking for the best site for carbon storage. We should look for acceptable sites. There are a lot of acceptable sites for nuclear waste, but if one gets caught into looking for the best site, there's an escalation that occurs, and we end up with a trophy site. Put in different terms, John Gibbons over the last couple of days has repeatedly said, well, without the drama. Well, if carbon capture and storage ends up like Yucca Mountain, where there's a best possible site, there's an escalation that causes time and is actually technically somewhat disingenuous. Now, the way this would happen to us at Yucca Mountain, and the way it might happen here, is that every time a scientist would discover a new uranium nanocluster, you know, there would be a breathless reporting of it, and the articles would always end the same way with, this raises questions about nuclear waste storage at Yucca Mountain. Even if the experiments had nothing to do with Yucca Mountain, how would this happen at a carbon capture and storage site? I'd put my money on the hydrologic, the uncertainty in the hydrologic codes. It's easy to imagine someone doing a calculation at, say, one of the fields that Roger talked about and saying, okay, we predict this, but we predict this, but we observe that. This raises profound questions about the viability of carbon capture and storage. What we have to do as scientists is work out what can be accepted. Is the deviation, the acceptable deviation, this and that? Is it this and that? Is it this and that? We have to be prepared for this. Now, when the Yucca Mountain license application went in, there was a big stack off in the corner, which was the chemistry section. That was the section I wrote. Now, when I started off, I'd been around the world. I knew a lot of geochemists. I swear by the end of Yucca Mountain, I knew them all. A lot of them worked for me. A lot of them had worked on the project before me. A lot of them were preparing legal briefs that I would have to deal with in testimony. So I would suggest that all of you look around you in the crowd, especially you students. You're going to see all these people again. A number of them are going to be on the other side of the witness stand. The point here is that we may see something as an unalloyed public good. We will not have a technical consensus. How to solve this? I really don't know. Starting early, though, is not a bad solution. All right, the last one that I'll hit here is the website. Let me have a show of hands. Who here has heard of the Waste Isolation Pilot Plant? Just a handful. I would urge you all to go to Google News and type in WIPP, because this is an excellent bad lesson that we want to avoid in carbon capture and storage. The Waste Isolation Pilot Plant is the only operating high-level nuclear waste dump in the world. It doesn't deal with the spent nuclear fuel, but it's plutonium, americium, a lot of bad stuff. It's down in southeastern New Mexico, which is probably why a lot of people haven't heard of it. All right, it opened about 10 or 15 years ago. No releases or anything until 6 weeks ago. 6 weeks ago, there was a fire underground. A truck caught a crankcase of a truck. Basically burst into flames. They evacuated the mine immediately, and a week later, there were releases that were spotted a kilometer away from the website. 17 people have since been found to have workers have been found to have radioactive contamination. Now, they haven't gone back into the mine yet, into the waste repository yet to see what went on, ostensibly because they didn't have real-time radiation monitors. Okay, there's two lessons here. First of all, we should never say there's going to be zero release from these sites. We should, on a technical basis, be able to estimate what is the maximum that might occur and what we can live with. Saying that no radiation release is going to occur, and then following it up with, oh yeah, radiation release has occurred, but it's less than an X-ray or whatever, it doesn't matter, you've lost credibility at that point. Now, having real-time radiation monitors, look, this is the only operating high-level nuclear waste dump in the world. For Lord's sake, why don't you have... The point here is that they should have planned for failure, planned for the truck, planned for maybe a rockfall. They don't know what happened to cause the release, though they know it occurred. We should do likewise. Now, I'm not a pessimist about this, and I agree with what Frank O'Keefe said yesterday morning. It's too late in the game to be a pessimist. If we want to avoid the surprises in the undiscovered part of the cave of carbon capture and storage, I would suggest that we focus on three concepts. 1, preparation. 2, patience. And 3, humility. Preparation would allow us to start working out what the real long-term monitoring should look like. We should be informing EPA what those regulations should be, because they're going to make a very big difference. We should also do preparation by having multiple sites, and we should avoid the escalation of individual sites into trophy sites. Patience, we shouldn't be surprised at the opposition we receive. Even if we all think it's wonderful, we're going to get technical opposition. It's going to be strong, it's going to be good technical opposition, and I'll bet a lot of it's going to come from our friends. Lastly, humility. We should expect failure, and we should plan for it. Thank you.
The next speaker is Peter Kelemen. He's a professor of geochemistry here at Columbia University, and he's a leader in carbon mineralization.
Hello, everybody. I don't belong here right now because we're at kind of readiness level 1, and we haven't stored any carbon. But so I'm happy to address this audience in any case. I've been working with a whole group of people who are acknowledged here, but I'm going to try and show you 30 slides in 10 minutes, so I won't dwell on it. I just did want to update this just so we can all see what we're looking at. This is global CO2 emissions as a function of time over the past century. The IPCC is shocked to inform you that the rate of emissions has actually increased in the past decade. This has been going on for more than a century. It's not shocking. It's happening at about 2% a year, keeping pace with the global economy. Doubling time is about 34 years. And if this were to continue, we would be emitting 100 gigatons by mid-century. Just for reference, 4 gigatons is the amount of oil that the oil industry produces and moves around on the surface of the planet every year. So if you think that we're going to do CCUS to account for a significant part of these emissions, you're talking about building a transportation infrastructure that's equal or to or larger than the transportation infrastructure for oil on the surface of the planet today. Okay, this is for Scott and Jason, so if you see them, you can tell them about it. London became the world's largest city in 1821 with 1.4 million people, and there was no central sewage disposal. The Romans did it, but the Londoners didn't. And so they gradually pushed past a safe threshold, you could say. They were throwing their poop into the street, as in this picture, and they also had cesspools in neighborhoods. And there were 3 large cholera outbreaks in the first half of the 19th century that killed tens of thousands of people. And they clearly overshot any sort of safe limit to throwing poop into the street. And then came the Great Stink. In the summer of 1858, it didn't rain much, and it became almost intolerable to stay in London. The royal court moved out, and Parliament considered moving out, but instead passed legislation. And so over the course of the next 10 years, they spent 2% of GDP annually and dug up every single street in the world's largest city to install a central sewage system. And I believe, I've read this, I haven't checked the data, that they're now spending about 1% of GDP in the London metro area to maintain their sewage system. Okay, so society is capable of recovering from overshoot, and furthermore, we're capable of sustaining costs of 1 to 3% of GDP to take out the garbage. Okay, just as an example of the garbage, if we do continue on the exponential growth trend that as economists tend to like, then we will probably be emitting 100 gigatons per year by 2050 or so, and that will almost certainly lead to 600 ppm CO2 in the atmosphere. Okay, so how might you get it out? Something we didn't hear about in the air capture discussion yesterday is the natural or engineered reaction of magnesium silicate rocks with carbon dioxide to form magnesium carbonate and quartz. It's a natural process that actually occurs very rapidly because ordinarily the peridotite is a rock composed mainly of the mineral peridotite or olivine. And ordinarily, peridotite is shielded from reaction with the atmosphere and surface waters by the Earth's crust. But when plate tectonics and erosion do us the favor of exposing peridotite on the surface, it is very, very far from equilibrium with the water, carbon, and oxygen fugacity on the surface. And this drives a very, very rapid reaction by geologic standards that ultimately forms, that ultimately forms magnesite plus quartz. Here's an example of carbonate veins formed in the subsurface in peridotite. By and large, we've found, to our surprise, in Oman that almost all of these record carbon ages of less than 50,000 years. We can talk about why that might be later if you want to, but they're very young, and by geologic standards, they're forming very fast. And on the surface, we see these giant travertine deposits. If you've ever been to Mammoth Hot Springs or the travertines around the geysers in Iceland, you know what these things look like, but the ones in Oman are bigger and more numerous. And when you put those two things together, you get natural uptake rates of 10,000 to 100,000 tons per year, or in the actively weathering horizon, about 1,000 tons per cubic kilometer rock per year, or it's easy to remember, a gram per cubic meter per year. There's experimental data that have been very recently verified by Grishma Gadikota here at this meeting, graduate student with Alissa Park, which show that the olivine carbonation rate is very sensitive to both temperature and the partial pressure of CO2. So here we illustrate the rate enhancement due to increased partial pressure of CO2 in these different curves and increased temperature on the horizontal axis relative to the rate at 25 degrees C and 1 bar of atmosphere. And so you see that you can get, if you can get to 185 C or so, and over about 70 bars partial pressure of CO2, you get a rate enhancement of more than 1 million. And if we then take the rate in Oman today and multiply it by 1 million, we end up with a gigaton of CO2 uptake per cubic kilometer rock per year. Now, nobody thinks that this is really achievable at that level of efficiency, but when you do a back of the envelope calculation like this, and you get a value of a gigaton per year, it kind of makes you sit up and pay attention. One thing that you get for this, so the idea here in the natural system, of course, is spontaneous, but if we think about engineering emulated approaches to the natural system, we'd like to take maximum possible advantage of the chemical potential energy that's inherent in this far from equilibrium situation. And one outcome that Bill Fife emphasized for olivine hydration, but it's equally applicable to olivine carbonation, is that, of course, you're condensing gas or fluid to form a solid, and so that's always exothermic near the surface. And so Bill proposed that you could get into a positive feedback loop where the reaction rate is dependent on temperature, but very rapid reaction involves heat. We've constructed a very simple model of this, which I don't want to go into in any detail, but we considered advection of cold fluid. You wouldn't want to have to heat up the fluid that you put into the ground. That would be very expensive. Thermal diffusion, that turns out to be negligible. And heating due to this reaction process, where here's the enthalpy of the carbonation reaction, and we have a rate, which is a function of temperature and the partial pressure of CO2 multiplied by a surface area term, which is red. Okay, so if you pump at 10 centimeters per year in this particular model, 25 degrees C fluid, 300 bars PCO2, that you can see the enthalpy of the reaction at 185 C having an effect, but the rate of change of temperature here on the vertical axis is predicted to be negative for any scenario. If in turn you reduce the flow rate to 1 centimeter per second, then you get into this self-heating regime where between about 125 and 250 C, this system is predicted to be self-heating. The enthalpy overwhelms the cold advection of the fluid. But you don't want this either, because if you turn this into a time series, you run up from here and then back down, so the rate isn't optimal. So instead, you would want to tune it, so 4 centimeters per second turns out to be just perfect. Aficionados will notice that this is an unstable steady state. Rate of change of temperature is 0 at 185 C. So if you fall away from that, the system's going to either heat or cool, but I would maintain at 10 to the minus 5 degrees C per second that a monkey with a lever could regulate this. Okay, now let's look at this scarlet letter, the surface area term. In the models that I was showing you, we assumed that was constant. Of course, it won't be. And so you can come up with a lot of scenarios where, because you coat reactive surfaces with solid reaction products and you fill porosity and reduce permeability and so on, this will exponentially crash. However, we do see rocks that are fully hydrated and fully carbonated in the geological system, so how does that work? And again, Bill Fife proposed that there's a feedback between the volume change that's due to adding volatile components to the solid phase and cracking. So if you get into that, you have big volume change, cracks the rock, allows more fluid to come in, causes more volume change, runs away. This is pretty analogous to salt weathering, which has been studied a lot by civil engineers. So in this case, this is a sandstone, which has had capillary rise of salt water into it, and then you have salt crystallization within this rock cylinder, which in turn breaks the rock. Here's a model of the same system where you gradually expose the rock to a reactant due to cracking, which in turn is due to diffusive reaction along the crack edges. And when we look in Oman at the carbonated rocks, we see patterns indicative of the same kind of hierarchical fracture and reaction process. All kinds of really cool textures, which I won't dwell on, but I can't resist showing. And here we have a rock that's completely carbonated. Every single magnesium atom in this rock has turned into magnesium carbonate magnesite in the dark gray. These lighter colored veins are quartz veins, and this bright mineral is a chromite from the mantle, just to ensure you that this really did come from the Earth's interior at one point. Here's a mountain. This layer of carbonated peridotite is 200 meters thick. This one is about 10 meters thick. There's 1 billion tons of CO2 in this mountain alone. So in terms of engineered solutions, one idea is that somebody gives us a fluid with a high partial pressure CO2. And you put that down in the ground. You might want to frack. You actually don't need to add bicarbonate because the pH swing due to fluid rock reaction is going to drive the pH up anyway. It's going to maintain high temperature due to the exothermic reaction process, and this is either a really bad idea or it will be self-cracking. In terms of cost, I don't see any reason why this should be substantially more expensive than any other subsurface carbon storage mechanism. It's a little more expensive at the front end because you'd probably want to frack. It's a lot less expensive at the back end because carbonate minerals, once you form them, don't go anywhere. Okay, so on the other hand, I'm pretty sure we're going to overshoot, and we're talking about negative emissions. And so how might you take maximum advantage of the chemical potential energy in this system? Well, if you could make thermal convection drive seawater through these rocks, we know from the natural system that you would return fluid with no carbon, dissolved carbon in it at all, to the sea surface, and then it would draw down carbon dioxide from the air. We know this can happen because it does happen. So here's a seafloor example of the same kind of system we see in Oman. There are subsurface magnesium carbonate veins and seafloor carbonate deposits forming as a result, pH 11 water being injected into the ocean and raising the ocean pH. This has been operating like the systems in Oman for more than 50,000 years. It's not clogging up. It's not running out of reactants. So in this case, you don't have to pay for CO2 capture. You don't have to pay for CO2 transport. You don't have to pay to grind any reagents. You don't have to calcine your uptake material. You just basically throw it away. But it helps to have a subsurface heat source. When you try and draw pictures of this, they end up looking a lot like a geothermal power plant. And in fact, you might want to try and generate some byproduct power from a system like this. In any case, it's limited not by the reaction rate per se, but by the supply rate, because CO2 concentration in seawater is so low. So it's basically limited by how much water you can get to flow through a standard industry pipe, about 3.5 meters per second. If this cost $1 million or so to set up and operated for 30 years, you would end up paying $40 a ton for that carbon uptake, or 0.1% of GDP per gigaton. You might run out of shoreline places to do this, but I just want to point out to you that roughly 10% of the Atlantic seafloor and the Indian Ocean seafloor and a lot of other places is composed of peridotite. with absolutely gigantic uptake capacity. So does anyone know James Cameron's phone number? Thank you very much.
Our last speaker is Jeff Fritz. He's coming from Princeton University in the Department of Civil and Environmental Engineering. He's looking at both theoretical and experimental approaches to CO2 storage and EOR.
Excellent. Thank you, everyone, for coming today. I'm going to give a very kind of broad stroke view to hopefully stimulate some questions about the current state of CO2 utilization, focusing mainly on EOR, some building materials, and then kind of give an outlook. So here is DOE's concept of all of the options for CCU, or utilization. You see at the center here is capture. So for any of these things to function, the assumption is that you're going to be using captured CO2. There was a lot of talk yesterday, or some talk, about liquid fuels and chemicals, and the liquid fuels being kind of the largest volume option in this case. But you see plastics and some of the things that were also talked about last night. A wide range of products, of course, and biofuels and bio-enhanced carbon capture options. But this reflects, of course, our carbon economy. And the motivation for doing utilization without a carbon tax or a price on carbon is that you can generate revenue for the captured CO2, with the captured CO2. And then also we've heard about market entry, and that you can demonstrate projects that could then be moved to scale when we do really need to become, and we do decide to take serious action against of putting CO2 permanently stored. But of course, these are a wide range of unproven technologies in a lot of cases, and uncertain energy balances and CO2 scarcity. I'm going to focus on the enhanced oil recovery and mineralization kind of indirectly. So we've heard a lot about EOR, enhanced oil recovery with CO2. This is a plot of current EOR, or up to 2012, where we're approaching 300,000 barrels per day of oil from CO2 EOR, which is about 6% of U.S. crude oil production. There's 130 CO2 EOR projects operating in the U.S. as of 2012. This is the amount of CO2 that was used in 2010 with EOR. In terms of kind of asking the question about a carbon balance of this operation, assuming that you have one of the kind of the more positive or kind assessments is assuming you have a closed loop operation where you have complete storage. You have 1 metric ton of captured CO2 for every 2.5 barrels of oil recovered. But in the US, for EOR, natural sources of CO2 provide 80% of that CO2 used back in 2010. You can see the sources here, natural sources, which dominate down in the Permian Basin, and then industrial sources. What is missing from this map, which I recently saw a map that should be coming into publication, looking at sources of industrial sources of CO2 that now have to report to the EPA. And if you accumulate these, you'll see that there is a major amount of CO2 being vented from these industrial sources. The other thing that you see when you look at it from that perspective is that there are places in the U.S. where there is a significant absence of CO2, not in the major conventional oil-bearing basins, of course, but that is one of the drawbacks or one of the limitations at this point. There's also limited CO2 infrastructure, and the natural sources are much more cost competitive. The DOE has in their portfolio projected that we will add 14 megatons of CO2 with new sources by 2020. One of those projects is the Kemper County IGCC, which is being under construction and is scheduled to come online in 2014, likely 2015, with pre-combustion CO2 capture. This is a 582 megawatt plant. That 65% CO2 capture is the goal. There's some question about kind of there's no mandate here. This is a capture goal, which would then provide 3.5 megatons of CO2 captured annually for EOR, which they have constructed a pipeline. But as many of you who follow this have probably seen that in the news, a $1 billion over budget at this point. There's this looming kind of ratepayer burden that has been approved for the utility to increase. So there's a lot of negative press surrounding this and negative feelings. Again, as was pointed out earlier, major government subsidies from DOE and through federal grants and tax credits. These will average out to $10 per ton of captured CO2 over 20 years. And of course, while there have been contracts signed, the revenue from selling the CO2 for EOR is to be determined. So I think there are some serious questions still about the value added and the revenue in this case in EOR. So now jumping on to building materials, you look at annual embodied energy of CO2 emissions from common building products in the US, where it's broken down in energy consumption and then CO2 emissions. You can see in the case of cement, which is the largest, that the annual CO2 emissions is almost twice what from the energy consumption. So that is because you have this chemistry is responsible for 55% of the CO2 release in the reaction to generate the clinker that's needed for Portland cement production, whereas the heating up to 1450 degrees C takes 45% of the fuel, which estimates are from around 1 ton of CO2 per ton of cement produced, which is why you get this massive contribution, which is 5 to 8% has been estimated in terms of all CO2, anthropogenic CO2, which is the third highest emitter. The other thing is the market is projected to double in 2050. So there are a number of projects related to trying to find alternatives to ordinary Portland cement to offset these emissions. You have binding phase based on carbonation. Instead of the hydration reactions, there's a company in Piscataway, New Jersey that's been funded by DOE to further develop a product that they say they already have. They have not open these materials out to, haven't shown the properties of these materials. Also using carbonates as supplementary cement materials. There have been a number of companies that have tried to make this happen. And then finally, one of the, where there's growing effort and growing activity is in the geopolymer cement, which you have a pseudo-zeolitic type structure. Also, one of the advantages is using waste products as precursors, using fly ash and slag. There's also commercial applications that have gotten up at demonstration scale in Australia, where they have done precast concrete. But this is still really a niche application, and there are formidable challenges to scaling. In terms of the carbonate additives, there's issues with mechanical strength, reduced mechanical strength. In the case of geopolymers and using carbonation, you have durability, questions of durability issues. And this is really where they kind of run into most of the problems, is demonstrating that they can meet the prescriptive code of the ASTM standards. There is a lot of work and a lot of attention going on to how do you accelerate tests and get those processes accepted by ASTM to accelerate how these things will behave in the field. So finally, just in terms of some thoughts to leave you with, there are opportunities to demonstrate distributed direct air capture and CO2 EOR, especially in terms of negative emissions, using these EOR sites. Also with carbonated building materials, where you could co-locate these sites. In terms of the EOR, robust MVA, as people have mentioned, is really, I think, an important step. And then in terms of the limited progress with scale-up of CCUS, points to the need for these negative mitigation strategies, which I think is an important argument to promote some of the research that people are talking about here. With that, thank you.